Hello, ladies and gentlemen! Herzlich willkommen! Добро пожаловать, друзья! My name is Andrei and I would like to assign this video to the topic of advanced meshing and calculation of rotated geometry parts. This video will contain 3 chapters. The first 2 chapters will deal with meshing topic. The third one will be about CFD analysis. Due to the fact that CFMesh in its free version cannot mesh rotating geometry parts or create meshes with motion, I will work with snappyHexMesh in this case. This is where we finally go different ways with CFMesh, and the choice falls on snappyHexMesh. I have already reported on this, see the earlier videos, for example advanced meshing with snappyHexMesh and CFMesh for Fluent, Start CCM and pimpleFoam, part 1 Antonov Antu or part 2 or other videos. CFMesh is a good mesher, but in its free version this mesher has too few application possibilities. As usual, we start with geometry preparation and defining the boundaries. I start with Salome. For that I push the button Run Salome. In our current study we will mesh and calculate a fan or blower. An example of such blower we can find in the internet. The electric air pump with 3 attachments. Blower pump from other electronics. This kind of blower we will investigate. Now I open the blower case. For that I go to geometry, go to desktop, blower, salome, blower HTF file. The geometry is quite simple. It consists of the rotor called walls rotation, this one, and blower housing, walls blower. The rotating zone defines the rotating area, and it is represented here, zone rotation. Everything inside this zone will be rotated. It is important to mention that the rotating parts should ideally have an axis of rotation that passes through the point 0, 0, 0, like it's done in this model. If it's not possible, then at least place the axis of rotation so that it lies on a point with integer coordinates and runs parallel to the x, y or z axis. I have also defined the outer walls where the fan is located. Walls outside. Looks like this. So I did not define this outer zone in block mesh because in block mesh this outer volume is mostly square or rectangular, and only with a lot of work can other shapes be in block mesh defined. Accordingly, I can define any outer contours with CFD software and then cover them with block mesh in form of rectangle or hexaeder. I will show you how I separate the boundaries in Salome. For this I import the step file. I go to File, Import step file, blower 2. Dimensions will be in millimeter specified. So now you have the complete shape. I go to the file and do the right click and choose the option create group. From now I start separating the boundaries. I will begin with walls outside. I choose them, add, hide selected, and the next three, add, hide selected. So I give them the name walls outside. Click apply. Then, in order to suppress these walls, I click on walls outside. I click add, Ctrl R, hide selected, and remove them. So now I want to choose walls rotation. For that I do the same operation. I click unnecessary walls, add, hide selected, add, hide selected, add, hide selected, add, hide selected, and so on, until I have this kind of geometry. So I do Ctrl R and remove the unnecessary walls. Now I select the walls rotating. I add them. I can also push Ctrl R and show only selected. So in order to see that only these walls are being selected. And now I give them the name walls rotation and click apply. So for the last walls blower or housing, I have to choose the previous selected walls, push the Ctrl R, hide selected, and remove them. So now I have only the blower housing. So I select it, click add, and now I give them the name walls blower. Now I have to click apply and close, and that's it. Next, I will export the boundaries in form of STL. For that I choose the necessary walls, including zone rotation, and export them as STL files. Here I can define export folder, so and now I can do the export. I enable the relative option and do everything absolute. So the export is done, and finally I will define the bounding box in Salome. So I click to the geometry, I go to inspection, dimensions and bounding box. Now we see the bounding box coordinates, x direction -5 and 17, in y direction -5 and 5, and in the z direction is -5 and +5. The geometry of the fan has been enlarged in comparison to the real blower geometry. So, for example, the diameter of rotation zone here of rotation zone is 3 meter. Inlet is here situated, has 800 mm diameter, and outlet blower here has 680 mm diameter. The distance between the rotor end and the rotating zone is 32 mm. I can show you. So if we have the diameter of rotating walls, and then we have rotating zone, this distance between both sections is 32 mm. I can write it. Now I can show it here. And the distance between the rotating zone and the fan inner diameter is also 32 mm, and it is the same in all directions. I can show you. For example, if we have the inner of the blower, the distance here is also 32 mm. So you see the distance of 32 mm is in all directions. This gap didn't just arise and has to do with mesh refinement and global cell size. In this case, the global cell size will be defined in relation to 32, or better to say in relation to 2 and its potential. For example, 2 times 2, 4, 2 times 3, 8, 2 times 4, 16, and so on. The distance should contain exactly one cell size between the rotation zone and geometry parts. This makes the mesh homogeneous and of good quality. In the same way, I dimensioned the geometric edges, wall thickness, so that they are also 32 mm in size and always contain one cell's init length. For this simulation, I am aiming for coarse mesh with total cells number between 2 and 4 million cells. The coarser the mesh, the larger the time step. This means you can calculate the time of 5 seconds relatively quickly with my powerful PC. The calculation will take up to a week. For the finer mesh, I can redefine the refinement level to the next finer level and be sure that from now exactly 2 cells will be defined between rotor, zone rotation, blower walls, and on the geometry itself. From now I close Salome and start my pimpleFoam template Excel tool and define all parameters for snappyHexMesh dict. So first I define the path to exported boundary files and put it in cell B1. For that I go to desktop, blower, Salome, export blower 2, copy this path and put here. Then I press the button STL Prepare. The tool defines 4 boundaries to which we assign the refinement levels immediately after bounding box definition. Bounding box coordinates are known. The global cell size should be selected so that we get between 1 or 2 million cells in the block mesh. 128 millimeters fits quite well. You see here, if we choose the cell size, global cell size 128, the cells amount in block mesh will be close to 1 million. The bounding box coordinates are given here. Here we have all refinement levels beginning from 0, global cell size 128, and ends by refinement level 10, 0.125 mm. Accordingly, we switch to STL files and define the refinement levels on the geometry parts. All walls receive refinement level 2 except walls outside. For blower, for rotation walls and zone rotation. And of course for surface refinement also 2 for blower, 2 for walls rotation and 2 for zone rotation. I click Save. Soon we will go back to snappyHexMesh dict worksheet and define further inputs. So the block mesh will be true, surface feature extract dict is also true, include angle 178 and write objects no. So decomposed part dict is true, the method will be simple, and we have 16 cores in X direction 4, in Y direction 2 processors, or 2 cores, and in Z direction also 2 cores. So snappyHexMesh dict is true, castellated mesh and snap true, and add layers are false. So merge tolerance is 1A-6. The geometry tolerance 1A-4. We have to define 2 refinement boxes as true, and then the amount number of refinement boxes 2, and also refinement cylinder also 2. The coordinates are known. I defined them before I start the recording section, and here you can only see the min max coordinates, points, and so on. Castellated mesh controls contain 30 million cells for global cell size or for global cells amount. Then we have numbered cells between the level is 1. Features will be true, and refinement surfaces option is also true. Here I can also maintain the location in mesh and location outside the mesh. So snap control will be defined as follows. Here is it important to say that we take explicit feature snap. That means that the snap will be done by using the feature block. That's why the feature block is also true. Mesh quality control settings will be default as usual. I choose here default. So as you know, I also have the definitions for mesh quality control of good quality and good geometry reproduction settings. If needed, please contact me. Finally, I press the button snappyHexMesh Dict and other dict creates. snappyHexMesh Dict. Now it's created here, and other dicts create. Other dicts are also created. I watched the snappyHexMesh Dict briefly. So we have here castellated mesh, snap through geometries shown here, and then we have refinement boxes, refinement cylinder, refinement regions defined as levels. So then we have castellated mesh control, including max global cells. So feature block, it has refinement level which we have defined before, and of course the surface mesh refinement which contains two levels. So then we have location in mesh, location outside mesh, allows freestanding zone faces through. It's very important because we have rotating zone faces. Then we have snap control, add layers not needed. For snap control, I can say we have here the explicit feature snap. That means snap is done by using the feature block. Feature block, these edges from surface feature extract dict will be refined. So now we have mesh quality controls, default, and everything seems good for me. So we have to come to an end of this chapter. I copy preform template files, copy and put them to the USB. So USB, not this, CFD projects, blower 2, new folder, preform template 2, then I copy export files where they are defined. Go to the desktop, lower, Salome, export blower 2, and HDF file. Look briefly on it. So maybe we can copy also CFD files and screenshot this one. So that's it. So I close the preform template file and save it before closing. The USB is ready. I close everything and that's it. See you in the next video in the Linux session. Bye bye.